Okay, we were looking at optimization, and remember that we came to optimization from state space search, and the way we did this was that we looked at the heuristic function that was used in best first search and said that this defines a terrain over which we use an algorithm called hill climbing, which is a local search algorithm as opposed to a global algorithm which best first search was, which means that the algorithm looks only at its neighborhood, immediate neighborhood in the state and or in the solution space, and moves to one of them essentially. And then we saw that local search algorithms can get stuck in local maxima or local minima as the case may be. And so, the theme for us at this moment is escaping from those minima. That how can we improve upon hill climbing? So, what does hill climbing do? Hill climbing does what we will call as exploitation. And exploitation of the heuristic function essentially, that it basically follows the heuristic function. It looks in around its neighborhood, and wherever the heuristic function is getting a maximum increase, or in other words in the direction of the steepest gradient, it makes one move and then repeats this process till it cannot find a better neighbor essentially. And in escaping local maxima, we said that one of the first algorithms that we looked at, or in fact the only algorithm that we have seen, is variable neighborhood descent. And what this algorithm did was that it tried out a variety of neighborhood functions. So, for us the neighborhood function is given by the move gen function, and we also said that we are moving from state space to solution space search, which means that we are perturbing candidate solutions to generate new solutions. And we saw that example with SAT, that you can flip 1 bit, or you can flip 2 bits, or up to 2 bits, or 3 bits, and so on. You can generate a variety of neighborhood functions. And what variable neighborhood descent does is that when it gets stuck, it does a series of hill climbings, and when it gets stuck at a local maxima or at a maxima, it does not know whether it is local or not. It increases the density of the neighborhood function and tries hill climbing all over again essentially. So, we want to look at different other approaches which will help us get around local maxima. So, in the process, when we are talking of optimization, we will use the notion evaluation. So, this is just particular to the optimization community. So, but you must keep in mind that we are talking about the same function, whether it is h of n or eval of n. It is basically a value that you get for a given candidate, and the task is to maximize, to find the candidate which has the maximum this value. So, in heuristic functions, if you are thinking of heuristic as a distance, then you want to find the state with the smallest distance, which is the goal state. Or if you have posed it like we did in the blocks world problem, that some heuristic function which has a maximum value at the goal state, then you are maximizing essentially. And so, instead of calling it heuristic function, we will call it eval function, but the process is still the same, that we want to find a node with the maximum value or the minimum value, the case may be. So, today let me introduce this, one of the most talked about problems in computer science, which is a traveling salesman problem. I am sure you are all familiar with it. So, I will just write the acronym here. TSP stands for traveling salesman problem, and it is one of the simplest problems to state and one of the hardest problems to solve essentially. Yeah. So, a traveling salesman problem is basically, the motivation is said to be to help a traveling salesman who has to visit many cities, let us say in one day or something like that, and come back to his home city and do the whole thing with some minimum cost in some manner essentially. So, I suppose everyone is familiar with the TSP problem. We will say that we have city 1 to city n cities, which we will also denote by 1 to n, just as a shorthand, easier to refer to essentially. So, we have these n cities 1 to n, and you have to go from one place to another essentially, one city to another without visiting the same city twice. Now, in practice, of course, in some problems it may be necessary for you to visit the same city twice essentially. So, for example, if there is a small island near the coastline, to go you go to that island from one city, let us say Chennai for example, and you come back to Chennai and then go somewhere else essentially. But we will ignore all those problems, and we will assume that the classic problem of visiting each city exactly once essentially is what we want to solve essentially. Now, in practice, a city network may not be completely connected, in the sense that if it is a road network, you may have roads from some cities to other cities and so on and so forth, but not, for example, a direct road from, let us say here to Nagpur or something like that. But we have indirect roads, in the sense that maybe you go from here to Vijayawada, and from Vijayawada you go to Nagpur or something like that. But in general, it has been found that it is easier to solve TSPs when the underlying graph is completely connected. So, we will assume that this is completely connected. And we can always convert a non connected graph to a completely connected graph by adding new edges and making sure those edges have very high weight, so that they never figure in the solution actually, but the solving process becomes easier. Now, TSPs occur in many practical problems. So, for example, drilling circuit boards. If you want to manufacture circuit boards, then you have to drill many holes on that board, and if you think of each hole as a city, then you have to visit all these locations, keep drilling holes essentially. So, we have something like a TSP to solve there, and such problems have something like thousands of so it's not uncommon to have a problem with 80,000 holes to be drilled and things like that, and then you can see that the complexity of the problem grows very quickly. So, what is the number of tours that we have? For if you have n cities, how many tours can we have for those n cities? So, we can have n factorial tours, and one of the notations that we will use for a tour is something like this. So, for example, if you have 9 cities, then a tour could be something like 2, 7, 1, 6, 4, 3, 8, 5 9. Yeah. So, a list of city names, or in this case city indexes or city numbers, gives you a candidate tour essentially. So, this is a tour. So, it says that you start at city 2, then go to city 7, then go to city 1, then go to city 6 and so on essentially. We can represent a tour in this fashion, and you can see that we can always choose the first number in n ways, the second one in minus 1 ways and so on, and that is how we get that number factorial n. But many of these tours are duplicates of each other. In particular, if I rotate this number, if you think of this as a number, I start with 7 and 2 comes at this end, then it is the same tour essentially, because remember that in this travelling salesman problem you have to come back to the same city. So, after 9 you are going to come back to 2. So, I could have started with 7 and written 2 here, or I could have started with 1 and written 27 here, and that would be the same this thing. So, you should divide this by n, because there are these n rotations that is possible, and in addition if I write it in the reverse order 9 5 8 3 4 6 1 7 2, then also we will assume it is the same tour. So, we will assume that the cost of going from city A to B is the same as the cost of going from city B to A. So, you have to divide further by 2. So, you have to divide by 2 n. So, what we get is n minus 1 factorial divided by 2. So, this is a number of distinct tours, which means no two tours are identical. Of course, in practice it may not be easy to recognize a tour as a distinct tour. So, we can say that we have about n factorial. The size of the space is n factorial essentially. How bad is the factorial function? So, remember that we had said when we were talking about SAT, we had said that a 100 variable SAT problem has 2 raised to 100, the size of the space is 2. So, 100 variable SAT has 2 raised to n, which we said was about 10 raised to 30, and we have been sort of talking about these large numbers and saying how big these numbers are, trying to imagine how big these numbers really are essentially. So, you must, whenever you get time, look at this book called Metamagical Themas, which is by Hofstadter. He is an author I keep talking about quite often, and one of the articles in that book, or one of the chapters in this book, is about how we cannot distinguish between large numbers. So, we cannot, if I say 25 billion or if I say 25 million, they basically appear same to you essentially. I mean, in the sense that we do not have a sense for large numbers essentially. If I say that it takes 10 raised to 27, let us say seconds, and if I say it takes 10 raised to 29 seconds, they sound almost the same to us, but in practice of course 10 raised to 29 is 100 times 10 raised to 27, and we sort of tend to lose sense of that essentially. So, we have seen that 10 raised to 30 are extremely large numbers, and if we have to explore all of them, it would be billions of years essentially. But a 100 variable TSP is about 10 raised to 157. So, TSP is much, the factorial function is much worse in terms of how fast it grows as compared to the exponential function. So, the SAT problem is exponentially hard. In fact, it is known to be NP complete. It was the first problem that was shown to be NP complete. TSP is worse than exponential. It is factorial, and factorial tends to go much faster. And you can see that the 100 variable TSP has about 10 raised to 157 different possible tours, and that is a number that we cannot even begin to imagine essentially. So, as something to compare with, we can say how many fundamental particles, let us say at some level electrons for example, are there in this entire universe. Does anyone have a idea? How many particles are there in the universe at some level of detail?
10⁻80 or something.
Yeah, it's in that range somewhere 10⁻75, 10⁻80 depending on what level you are looking at. So, the total number of particles in the universe is about 10⁻80. Each of them was a supercomputer examining billions of states per second. We would still need billions and billions of years. So, these are the very large numbers that you have to tackle, and that is why you cannot even hope to solve this completely. You cannot even hope to find an optimal solution for something like TSP, and in that sense many people call TSP as the holy grail of computer science, that how to find good algorithms to solve TSP is a great motivator essentially. Now, one thing that we are talking about, so what is the problem? The problem is that we have to find a tour such that the cost of the tour is minimal essentially. That is the problem essentially. Now, the cost of course depends on the individual distances between. So, distance city I, distance from I to j, what kind of a function are we using for distance function? Much depends upon that as well. If we assume that this distance function is arbitrary, then of course the problem is completely hard to solve essentially, and then we have to go by this thing. But sometimes the problems are not so arbitrary, in the sense that distances are not necessarily arbitrarily. So, one of course example is simple example is the Euclidean distance. If the distance is a Euclidean distance, so for example, if you are manufacturing a circuit board, then you can think of the distance as a Euclidean distance, and then at least intuitively you can imagine that you will be able to find an optimal solution. So, supposing it was a grid and you have to drill many holes in the grid, then you can at least hope to say that I will find a good solution, if not necessarily an optimal solution. Now, it turns out that for, so Euclidean distance we will call it a Euclidean TSP. It uses the Euclidean distance as a distance measure. It turns out that if the problem is a Euclidean TSP, then you can solve it in polynomial time, not optimally, but what the community calls as approximate solutions. So, you can find an approximate solution in polynomial time, and you can specify to what degree it is approximate. So, it is something like 1 plus 1 upon c or something like that times the optimal cost. So, in polynomial time you can find very good solutions, and you can put a bound on how bad they can be essentially. Apart from Euclidean distance, we can say that the distance should satisfy what we call as a triangular inequality. Which is a weaker condition than Euclidean. Euclidean distance also satisfies triangular inequality, but what triangular inequality says, that if you were to imagine a triangle between 3 cities, then the distance between or the length of one side is smaller than the sum of the lengths of the other two sides. So, that is this is known as the triangular inequality, and if the distance function satisfies the triangular inequality, then also it is relatively easier to solve. Easier to solve meaning you can find good solutions faster, you cannot solve it optimally essentially. Then we have something called the geographic TSP. So, imagine that you are one of those globe trotting executives who flies from here to Delhi and from Delhi to Tehran and Tehran to Budapest and so on and so forth, going all over the world. Then your domain is a spherical domain, the earth is a sphere as we all know now at least, and distances do not necessarily are not, we cannot talk of Euclidean distance. So, we have to talk about distance on the curved surface. So, that is a slightly different problem, and people have tried to solve these kind of problems. Okay. Now, interestingly, you must look up for this website, it is called TSP lib. Okay, so I do not remember the address, but you must look up for TSP lib website. It is a website maintained in one of the German universities, and it has got a collection of very interesting TSP problems. So, there is a problem of all European cities, for example, and some circuit board problems and things like that. And more interestingly, it has got problems in which somebody has taken the trouble to find the optimal solution. So, if you have a problem of 15,000 cities for which the optimal solution is known, then you can write some algorithm, a heuristic algorithm that we are exploring, and compare your algorithm with one of those with the actual optimal solution. So, this has optimal solutions. So, there are examples, big examples with their optimal solutions given, and so you could use that as a benchmark to see how good your algorithm is essentially, and we probably give you one exercise along those lines essentially. Some of those optimal solutions, see, the only way you can guarantee an optimal solution, and we will study optimal solutions a bit later, is to say that, I mean, this sounds like a circular argument, but to say that there is no better solution which is possible essentially, and if you can guarantee that there is no better solution, then you have an optimal solution. And it has taken them, if you look at some of the references, for example, this book Michaleves and Fogel, something like thousands of computing years of computing time. So, they have many machines working in parallel, and then they compute this exhaustively enumerating all TSPs and finding optimal solutions. So, you must go and look at this site which will give you optimal solutions. So, today let us spend a little bit of time. So, I have brought TSP here because one of the things we want to do is look at this variable neighborhood descent again from and see how TSP can be solved using this essentially. So, basically the idea being that what are the different neighborhood functions that we can construct. But before we come to that, so remember that we had said that there are two ways of solving problems. One is constructive and the other is perturbative. So, in constructive methods we construct a solution bit by bit, and that is the whole state space search that we started with. In perturbative methods we take a candidate solution and perturb it to look at another candidate solution. So, we did this for SAT, for example. We said that any bit string is a candidate solution, then you can change some number of bits, which is the perturbation you are doing, and look at another solutions. But you can also construct a solution edge by edge, if you want to say. So, let us first look at some algorithms for constructive solving the TSP with constructive methods, and then we will come to perturbative methods, in which case we will look at variable neighborhood descent and whatever other algorithm that we are going to look at after that. So, for example, given a set of cities, so let us assume that we are working in this Euclidean space. So, the actual distance is the distance. What kind of algorithm can you think of? Or you must have tried something sometime. So, the simplest constructive method is to try to simulate what you would do if you were doing this in the real world, so to speak. So, you start with some city, let us say this one, and then look at its neighborhood. Now, remember this entire set is a neighborhood because we have assumed that our graph is completely connected essentially in this case. But when we come to perturbative methods, we will look at smaller neighborhoods where all those. In this here the neighborhood is different in the sense that it is not a candidate solution, but it is a neighboring city. So, you go to the city which is nearest to it. So, let us say you go from here to here, and then you repeat this process. You go to the nearest city, you go from here to here, then you go, I mean it looks like this is the nearest, and you will get some solution, right, and so on. So, this is one simple heuristic algorithm. It is a greedy algorithm. It says start at some city and go to the nearest neighbor, then from there go to the nearest neighbor and so on and so forth. Now, obviously, in some situations it will give you a very good solution, if not the optimal solution. But you can imagine that what will happen with situations where I have a city somewhere here. If I have a city somewhere there, what will my algorithm do? Ideally, what should it do? It should go from here to that and come back here and then resume its thing, but it will not do that because my algorithm says go to the nearest neighbor. So, I will go from here to here, then I will go from here to here, and from here to here, then here, here, here to here, here to here, then I will go there and then I will come back here. So, obviously, you can, this is just to illustrate that this algorithm will not always give you a optimal solution, but it will give you, depending on what kind of problem it is, it will give you a reasonably good solution essentially. Now, a simple variation to this is that instead of thinking of going like this, you can think of extending your tour. So, at any given time you have a partial tour, right. So, let us say we have done only till this much. And instead of saying that this is a one directional thing, you can say that you can think of it as going in both directions, and then you can say you can extend at either end of the tour. Instead of saying that only extend at where you were trying to simulate a physical person moving around, you can say you can whichever end of the tour has a closest city, extend that end. That is just a simple extension of that essentially. So, I am now, how do you talk about cities like this which are far away from the rest essentially. So, one algorithm, so I am not writing these things, but any of, if you look at any textbook on TSP, they will talk about these algorithms. You could say that I will splice this. So, in the sense that supposing I have already constructed this tour, which is not a very good tour, but I have constructed it and I am only left with that city. Instead of going from this place to this place, what I will do is that I will find out which point in the tour is closest to this city and connect that with this, and then break this edge and connect this with this. So, this will give me some improvement essentially. So, that is, but obviously, every time we do that, the complexity increases, because notice now that if you write a general algorithm for that, you will say that for every new point in the city, which is the closest point in the tour. So, you have to inspect the whole tour. So, complexity will go up by a factor of n in that case. So, this is one set of constructive algorithms for solving the TSP. Another popular thing which is known as the greedy heuristic says that you sort the edges maintain a sorted set of edges and work with edges instead of working with cities essentially. So, you can now imagine what the algorithm is. It says that you have all the edges that are available to you in this thing. So, pick the shortest edge that is available to you and add that. So, in this example, for example, it could be this one. So, this could be my first edge that I add because that is the shortest edge. Then the next shortest could be this one, then it could be this one, and so on and so forth. So, this is a different algorithm. It is sorting the edges. So, you sort them once and then you pick the shortest edges. The hope is that you will pick all the small edges, because for the optimal solution, the more the number of shorter edges, the more likely it is to be optimal essentially. Obviously, when you are doing this greedy heuristic, you have to be careful that you do not have a loop on the way essentially. So, if you have connected some number of cities and if the next shortest edge is forming a shorter loop, then you should not take that edge essentially. So, that is one thing you should do. Then there is another heuristic called the savings heuristic. And all these are, available in many books. The saving heuristic says that first construct n minus 1 tours of length 2. So, let me illustrate this with this example. You take some arbitrary city and you construct tours with every other city. So, I will just take a smaller example. So, there is some city and from there you are constructing this. So, there are in this example there are 5 cities. So, I have constructed 4 tours of length 2 and then you merge 2 tours . So, how can you merge 2 tours? So, for example, I can say that I will merge these 2 leftmost 2 tours. So, I will take this one from here, I will take this one from here and I will delete this edge and I will delete this edge and I will add an edge here, new edge here. So, the only question is which 2 tours should I merge, and that is where the name comes from, savings heuristic. It says select that pair of tours in which you get the maximum savings. What is the savings? That your length, you had 4 edges in this to start with. So, you add up the lengths. So, L1, L2, L3, L4 and now after merging you have L1, L4 and a new one, let us call it L5. How much is the saving? How much is L1, L4, L5 better than L1, L2, L3, L4? Choose that combination which gives you the maximum savings. So, now that you have merged these 2, then you could merge this larger tour with this third one, for example. So, you could delete this edge and add this edge and add this one and so on and so forth. You keep merging. So, in n minus 2 merge operations you will finally get the tour essentially. Again, it is a heuristic algorithm, not guaranteed to give you an optimal solution, but in general all these algorithms give you reasonably good solutions for Euclidean TSPs at least essentially. So, let us now go to the perturbative approach. What does perturbative approach says? That you take some candidate and generate its neighborhood essentially. So, which is kind of different from this. Here you are constructing the tours gradually, here you are saying I have one tour given to me and I am going to produce a set of neighborhood tours and choose one of them essentially. Exactly like what we did in SAT, I have a candidate solution, I will perturb it by changing some number of bits to get new solutions and move to that new solution. So, the hill climbing like algorithm we are approaching now. The question is, what are the neighborhood functions that we can talk about here? Can you think of a, so given that tour for example 2, 7, 1, 6, 4, 3, 8, 5, 9, how can I generate a neighborhood around that? What is a property that a tour must satisfy? That it basically should be a permutation of those n numbers essentially. So, essentially you want to generate some new permutations and explore one of them essentially. Sorry? Swapping? Okay, swapping adjacent numbers would give you a new tour. So, instead of saying this, so I can pick two any place and swap two numbers. So, for example, I can replace 1 6 by 6 1, that is what you are saying. So, that is one. So, you can imagine how many such moves are possible. You can make n minus 1 swaps here. So, this will have n minus 1 neighbors. So, either the first two or the second two or the third, like this. So, you can swap. You can generalize that to something which we call as a two city exchange. And what that says is that take any two cities in the tour and exchange their positions. So, this is a particular case of that. It says that take two adjacent numbers and exchange that. This operator says that take any two cities and generate this thing. So, how many neighbors will this have? I can pick NC2, two cities in NC2 ways, and for each way that I pick, there is only one neighbor I am going to generate, because I can only exchange their positions essentially. So, I will have NC2 neighbors essentially, or I can have 3 city exchange. What this says is that take out any 3 cities from the tour and put them back in some different order essentially. So, I can pick them in NC3 ways, and then I can put them back in 3 factorial minus 1, because 1 I do not want to put it back in the same order. So, 3 factorial minus 1 order. So, I will generate that many this thing. So, what is this two city exchange doing? If I have a tour like this, then if I am going to exchange this one with this one, for example. Now, what it means is that I was going in this order, but now I am going to go, instead of this I am going to come here, and from here I am going to go there. So, this will go away, then instead of coming here I will go like this. So, if you must visualize this is what happening when I am exchanging this city with this city. Originally it was a circular looking tour. Now, because I have exchanged the position of these two cities, from here I am going to go here, from here I am going to go there, and then continue here, and then this something similar will happen essentially. Now, it turns out that city exchanges are not the best way of thinking about things, but edge exchanges are kind of easier to think about. So, for example, I have two edge exchange. It says that remove some two edges from your tour and insert two new edges instead of that. So, let us see what this means. Supposing I have a tour like this, or let us say I have a, I am just drawing them in a circle because it is easier to this thing, but in practice of course it is going to be sort of distributed over some space. I mean, cities are never arranged in a nice circle like this, but it is easier for me essentially. So, one of the things that we would want to do is that this Euclidean TSPs is to generate random problems, which means take a two dimensional space, let us say a computer's monitor screen, and randomly place cities there, and then say find the optimal tour for that essentially. Okay. Now, if I have a tour like this, so ideally if I have a tour which is something like this, you can see that I have two very long edges in this tour. If I could somehow remove them and replace them with two shorter edges, keeping it as a complete tour, I can transform this problem into another problem in which instead of this edge and instead of this edge, I add this edge, and I add this edge. So, what have I done? I have deleted 2 edges from my tour and replaced it with 2 more edges, and there is only one way I can do that essentially. If I delete any 2 edges, I have only one new tour that I can create in this example. How will I do this 2 city exchange, 2 edge exchange? So, let us say we have that tour something like that 2 7 6 5. Supposing I have a representation like this, how can I implement 2 edge exchange? Okay. So, anyway, so it will not come. So, once you know the answer, it is simple. Essentially, you take a substring here and reverse the substring. So, 2 7 4 5 6 1 3 9 8. So, let us see whether it is really doing what we are saying it is doing. So, which are the 2 edges that I have removed here? The edge that I have removed is one from 7 to 6 and 4 to 1. The other edges remain the same, because from, so here instead of going from 7 to 6, I am going from 7 to 4. And 4 is still connected to 5. Okay. So, maybe I should draw this. This is my cities. So, I go from 2 to 7, 7 to 6, 6 to 5, 5 to 4, 4 to 1, 1 to 3, 3 to 9, 9 to 8 and 8 back to 2. That is the last step. This is the tour that I started with. Now, I am saying just rotate this substring 654 and that gives me this tour 2 7 4. So, let us just follow the tour. From 2 I am going to 7 again, from 7 I am going to 4, 4 I am going to 5, which is part of the same tour, remember, notice. From 5 I am going to 6, from 6 I am going to 1, from 1 I am going to 3, which is also part of the old tour. Then from 3 I am going to 9, 9 I am going to 8. So, everything, all the edges except for this 1 to 4 edge and 7 to 6 edge has been replaced. So, I have taken out this edge 7 to 6 and 1 to 4 and replaced them with this edges which goes from 7 to 4, which is this edge, and which goes from 1 to 6, 6 to 1, 6 to 1, this new edge. So, this is this one and this one is the new edge that I have introduced. So, rotating a substring will effectively do a 2 edge exchange for you essentially. Why is this intuitively more appealing than city exchange? I hope it is intuitively more appealing than the city exchange, because it is the edges, it is the edge cost which adds up to the total cost of the solution. So, what would you ideally want to do is to inspect your solution, and of course, between every 2 cities there is an edge cost. Pick those edges which seem to be very high cost and replace them essentially. So, the original example that I had drawn, which was like you go some tour like this. So, if you have some tour like this where you are going like this, then these 2 are very long edges. If I remove them and replace them with this, I will get a shorter tour. So, in that sense, manipulating edges is more appealing, because you can at least apply the heuristic of removing very long edges essentially. So, 2 edge exchange is just one example. We can look at 3 edge exchange. So, 3 edge exchange So, you must compute how many neighbors that there are and so on. So, you can pick 2 edges in n minus 1 C2 ways, and then you will get n minus 1 C2 successors. In 3 edge exchange, let us say this is a problem, this is the original tour given to me, and I am removing these 3 edges. So, one is this one is this one, and one is this one, and now you can see that you can put them back in different ways. So, one way you can put them back is that you can connect this to this from here. So, you must be careful not to form a cycle. So, from here I cannot go to this, so that is not allowed. So, from here I can go to, let us say this, and here I can go to this. No, something is wrong. No? Here there are 3, so I can't do this. So, okay, I can put this here, then from here I can go to this, and from there I can go to this. Okay, so I have a new tour essentially. So, it turns out that there are 4 different ways to put them back. So, let us try one more, and I will leave the other 2 as an exercise for you. So, you understand this notation, okay, it is kind of a shorthand. This is some tour with some n cities, but we have drawn only 6 cities representing those 3 edges that we are going to remove. So, this edge we are removing, this edge we are removing, and this edge we are removing. Rest of the tour remains the same, but we are putting back 3 edges in slightly different ways. So, instead of this, now I can, instead of going from here to here, I can say okay, go from here to here, then from here you go like this, and from here you go like this. And there are two more different ways of doing it. So, I will leave that as a small exercise for you. So, 3 edge exchange, if you take out 3 cities, 3 edges, you can put them back in 4 different ways, and you can take out 3 edges in n minus 1 C 3 ways. So, into 4, these many neighbors you get essentially. So, what I am trying to illustrate here is that when you treat the TSP as a perturbative problem, you take any candidate solution and you can generate a neighborhood of candidate solutions around it using some number of city exchanges or some number of edge exchanges, and they are neighborhood functions of different density essentially, which means that you can apply the variable neighborhood descent function essentially. So, I am not writing this algorithm again. This variable neighborhood descent basically says that if you have a set of neighborhood functions arranged in a order of increasing density. So, by density means how many neighbors does a given candidate have. So, if a candidate has, let us say 5 neighbors, or if a candidate has, let us say 12 or 15 neighbors, then this neighborhood function is more dense than this one essentially. And why did we want denser neighborhood functions? Because it is less likely that the best amongst them is a local maxima essentially, or rather it is less likely that the given node is a local maxima, which means it does not have a better node surrounding it. So, there are the more the nodes surrounding a node, the more the likelihood of a better node existing if there are better nodes in the space essentially. So, the idea of variable neighborhood descent is that to start with the simplest neighborhood function. Why do not we want to work with the most dense function first? Because the cost of making a move is proportional to the number of neighbors that you have, because you have to inspect all the neighbors and then pick the best amongst them. So, like in SAT, if every if you can change any number of bits, then it amounts to doing the complete brute force search. We do not want to do that. We want to start with sparse neighborhood functions, move on to denser functions, and so on and so forth. So, in today's class, basically what we have done is looked at the TSP problem, and we have not really looked at the new method for escaping local maxima, which we will do in the next 2 or 3 classes. But when we are doing that, we will keep in mind how to solve the TSP. So, remember that this kind of this thing. Just a quick comment about this 2 city exchange. Remember, this was a 2 city exchange. I exchanged this city and this city, and as a result I added these 4 new edges, removed 4 edges because the neighboring edges from here, and added 4. So, you can see that this is a particular case of 4 edge exchange essentially. In practice, of course, if you remove those 4 edges, you can put them back in many different ways. So, 2 city exchange is just a special one of the cases of those 4 edge exchange, which is going to give us a denser function essentially. So, the more the cities or the edges you remove, the more the ways you can put them back in, and the more the ways you can remove them in, and they give you denser functions. So, that is one mechanism for doing that. Okay, so, I will stop here. We will, when we come back, we will look at a new algorithm for trying to escape local maxima. How can we escape this local maxima? That is going to be our objective in the next few lectures. Okay.